welcome to another module in this massive open online course. So, we are looking at different quantization schemes, right. We have looked at the uniform quantization, the Lloyd-Max quantization, and we have also looked at companding, right, different compressors. In this module, let us look at delta modulation, all right, which is a different form of quantization, all right, that is converting a continuous valued analog signal, right, sampling it, converting the continuous valued analog samples into a set of that is mapping them to a set of levels belonging to a discrete set, all right. So, that is a different quantization scheme which is termed as delta modulation. Okay. So, we are going to look at a different quantization scheme or a different modulation scheme, delta modulation. Modulation in the sense pulse amplitude. Here also we have pulses whose amplitudes are modulated, but we will see there is an interesting difference. So, what we have is we have a continuous message signal, and in delta modulation what we try to do is basically, if I have to explain it intuitively, we build a staircase approximation to this continuous message signal. So, we try to express it, as you can see, basically as a staircase kind of, right. So, we express it, right. So, this what we are trying to do is we are trying to build a staircase kind of approximation. If I remove this thing, right, what we are trying to do is we are trying to build a staircase approximation to a continuous message signal. We are trying to build a staircase approximation to a continuous message signal. Okay. And how do we do it? Instead of quantizing the message signal, instead of quantizing the samples of the original message signal, we quantize the differences of the samples of the message signal, and we are going to illustrate this shortly. So, the key principle in delta modulation is, instead of quantizing the samples, quantize the differences between the samples. Instead of quantizing the samples, quantize the difference between successive samples. Quantize the difference between successive samples. Now, what is the advantage of that? The advantage is, remember, the signals that we are trying to quantize, sample and quantize, are smooth signals, alright. So, the signal is varying slowly, right. So, the signal sample might be large, but the differences between successive samples is small. So, we are trying to quantize so if you have a quantizer of fixed resolution, that is a fixed number of bits, when we quantize the differences which are small, the dynamic range of the differences is small, right. So, naturally the quantization intervals can be very much more finer, the quantization intervals are smaller, which means the quantization is much more finer, therefore, the quantization error is lower, which leads to an improved performance, alright. So, let us note that. So, what we have when we have a continuous signals, we have continuous, typically we have smooth continuous waveforms, which implies that the difference of signal samples which implies that the difference of the signal samples is small. Now, that implies that the dynamic range of the difference the dynamic range of the difference between successive samples is very small. Okay. This implies that we have a finer resolution and lower quantization error. This implies we have a finer resolution and lower right. See, if we have a quantizer with resolution of b bits, number of levels is 2 to the power of b, right. So, b bit resolution implies number of levels equals 2 to the power of b. So, the idea is if the dynamic range is large, so the number of levels is same. So, if the dynamic range is large, then the quantization intervals are going to be wider, that is 2 to the power of b levels in this 2 to the power of b intervals in this large dynamic range. If the dynamic range is small, then we have the same number of intervals. So, since the dynamic range is small, the average width of each interval is going to be smaller, which means the quantization is finer, right, the quantization is finer and therefore, the quantization error is lower. That is the principle of delta modulation. Or one can also say that if we keep the quantization error constant, if we lower the dynamic range, right, if for the same quantization error we can lower the number of quantization levels. In fact, we can lower the resolution of the quantizer, right. If we lower the number of quantization levels, basically we are lowering the level of the resolution of the quantizer, alright. So, basically since the dynamic range is smaller, so the other way to look at it is lower dynamic range. So, this also implies that lower dynamic range implies, well, implies we need lower number of bits for quantization, which implies that the bit rate implies that the bit load implies bit rate can be reduced. Bit rate meaning the number of bits output per sample. So, bit rate can be reduced drastically, right. So, bit rate can be reduced for the same code while not increasing the quantization error, alright. And in fact, in delta modulation very specifically we are going to show that we are going to employ only a single bit for the quantization. That is the most important aspect of delta modulation. Delta modulation is efficient because the quantizer resolution needed is only a single bit, and in fact delta modulation reduces this bit resolution required drastically. So, in delta modulation resolution of quantizer is resolution of the quantizer. In fact, we need only a single bit, as we are going to show. In fact, we employ only a single bit. This is the single bit for in fact we employ only a single bit before quantizing. That is the important aspect of delta modulation. Okay. Now, how do we do it in delta modulation? Okay. Let us say MQN minus, so let us start with Mn, we know Mn, Mn is the sample at time instant n, this is the sample at time instant n. Now, let MQN minus 1, okay. So, MQN minus 1, this be the approximation. Now, we are going to show how we derive this MQN minus, so Mn we get from the sampling, MQN minus 1 be the approximation at time instant n, approximation to Mn at time instant. Therefore, the error, so we have Mn which is the sample value at time instant n, and we have MQN minus 1 which is approximation, alright, the quantized approximation to Mn at time instant n. Okay. And therefore, what we have is we have the error En will be equal to, this will be equal to, well, Mn minus MQN minus 1, this is the error, right, sample minus the approximation. Now, we are going to quantize En and we are going to do that with 1 bit. So, now we are going to quantize, observe that we are going to quantize En. So, therefore, what we are going to have is we are going to have EQ of n, that is the quantized error, equals delta times sine of E of n. Okay. So, EQ of n, notice that EQ of n, this is the quantized error. So, we are quantizing not the sample, but we are quantizing the error, quantized error. Sine function is basically, let us use the simplified version of sine, sine function of x equals, well, let us say this is equal to, this is equal to x if, well, this is equal to plus 1 if x greater than 0, minus 1 if x less than 0. Of course, at 0 it is 0, but we do not care about that single value. So, which means this can only take depending on the sign of En, if En greater than 0 implies En greater than 0, this implies basically that you can see that EQN equals plus delta. On the other hand, En less than 0, the naturally sign of En is minus 1, less than 0 implies EQ of n is minus delta. So, now you can see EQ of n can only take two values, either plus delta or minus delta, alright. So, only two values, therefore, the number of bits required is 1. Okay. So, let us note that. So, En can take only two values, or EQN, which is what we are quantizing, not En, remember EQ of n. So, En is the error and we are quantizing the difference, that is the difference, we are quantizing the difference. EQ of n can only be plus delta or minus. So, this is basically your plus or minus delta, hence only implies only two levels, plus delta minus delta, and therefore, only one bit and therefore, only one bit, only a single bit, only one bit is required for quantization. Since we are using only two levels, we are using only two levels, therefore, only one bit, only a single bit is required for quantization. Okay. So, this is your quantization, and now how do we reconstruct the approximation? Now, we have MQ of n, which is approximation at time n, which is also, in fact, if you think about it, the reconstruction at time n. This is MQ of n minus 1, MQ of n minus 1 plus EQ of n. Okay. So, this is the step, and in fact, this is the key step. There is a quantization. So, in fact, we can number the steps. Let us number the step. This is step 1, we reconstruct the difference. This is step 2, quantize the difference. Okay. So, step 1 is basically difference, step 2 is basically quantize the difference. Quantize the difference, and step 3 is basically what we have in step 3 is basically reconstruct the prediction, which is MQN, which is a reconstruction, but you can also say reconstruct, because this forms the prediction or approximation for the next time instant, approximation for the next time, and then this process will continue in the loop. All right, this process will continue in the loop. All right. So, let us see how this works. If I have a signal MT, I have a signal MT at time instant n, I have an approximation. Let us say I have an approximation at time instant n, I have an approximation. Okay. So, this is basically at time instant, let us say n minus 1, time instant n minus 1. Now, this is let us say time instant n. Okay, this is time instant n. Now, at time instant n, this level is MQ n minus 1. Let me write it clearly. This is MQ n minus 1, which is the reconstruction at time instant n minus 1, and which forms the approximation at time instant n. Now, if you can see Mn is greater than MQ n minus 1, greater than MQ n minus 1, which means the error Mn minus MQ n minus 1 is greater than 0. Remember, this is your E of n, this is the error. So, this is greater than 0. Remember this, if you look at this part here, this part is your E of n. So, E of n is greater than 0, which implies EQ of n equals delta sine of E of n. Okay. Now, since E of n is greater than 0, sine n is E of n is positive. So, this is simply delta. So, EQ of n is delta. So, that is basically your delta, that is basically your delta. So, this is of height delta, and so MQ of n minus 1 plus EQ of n, that gives the reconstruction. So, that will be your MQ of n. that gives the reconstruction. So, this is how you obtain the staircase approximation, and then subsequently we have the difference, we do that at every time instant, you see we can approximate. Now, obviously if En is negative, if the error, that is m of n minus mq n minus 1 is negative, then delta sign En. So, En is negative, delta sign En will be minus delta. So, obviously the staircase will go down. When delta is positive, the staircase will go. So, you get a staircase approximation of the signal. So, this is how you are getting a staircase approximation of the signal. So, this is how you are getting a, this is your basic staircase approximation of the signal. This is your staircase approximation of the original signal. Okay. And now you can see what is being quantized, only the error is being quantized in only one bit. EQ of n is either plus delta or minus delta. Okay. So, EQ of n is either plus delta or minus delta. So, this is the difference is encoded in one bit. Okay. So, this difference is encoded using one bit. This is so either we have, let us say, plus delta corresponds to 0, the level minus delta corresponds to information bit 1. Now, corresponding to, for instance, now we have this difference sequence delta minus delta minus delta delta minus delta, corresponding to this we can have an encoded bit sequence. So, delta corresponds to 0 0 1 1 0 1 so on so on. So, this is the encoded signal, and this encoded signal is either stored, if you have storage device as a stored, or transmitted. And for the purpose of storage, you can see that we are now achieving compression, because we are able to use only one bit to characterize the signal. So, remember this also gives us compression. In fact, there is a lot of application even in applications such as signal compression, that is for instance speech compression or image compression. So, this gives us an efficient way not just to quantize, represent the signal, but also to compress the signal, since we are using only one bit. So, this can also, so interestingly in fact, this can also be used for, this encoding can also be used for, realize this can also be used for signal compression such as speech compression, or image compression, etc. Okay. So, we have the signal, the error is quantized to 1 bits and it is either stored or that is encoded into a single bit, that is plus delta is 1 bit, that is plus delta is 0, or for example, let us say plus delta is 0 and minus delta is 1, and this encoded bit stream is then either stored or transmitted, that is the delta modulation. Alright. And in the subsequent module we will look at how to reconstruct this signal, how to reconstruct the original signal from this encoded bit stream. Alright. So, we will stop here. Thank you.